All right, exponential log function derivatives. All right, here we go. This is the derivative of an exponential function. So anything in the form of a to the u has a to the u repeated in the derivative, but then it's followed by the natural log of whatever that a was, and then also followed by the chain rule of whatever the u part was. So it's not a hard derivative, but if I'd asked you that before you walked into class today, you maybe didn't remember. Like yesterday, I forget, somebody came up with, it was Allie, I think, you had remembered what the log derivative was, I think. Was that you? 1 over x, right? Okay, but exponential, like it's not a hard derivative, but I don't know if you would have like totally had it remembered before you come here today, but it's a pretty easy one to do. So e has its own particular subset version of that. So if we apply that, it would be e to the u times the natural log of e, and then the derivative of u with respect to x, which really is just e to the u du dx. So that's a subset of that where the natural log of e isn't necessarily like explicitly written, but we understand that it's there. All right, so our first example should go pretty quickly if we are finding the derivative with respect to x. So it will be 3 to the x squared parabola as itself, as its own function, followed by the natural log of 3, followed by 2x. Now, what you don't want to do is take a fairly easy derivative like this and then do some like illegal things. So I have seen in the past students try and simplify this and tell me that this is the natural log of 6x because they're combining the 3 and the 2x as multiplication. So one way you can avoid that mistake is by putting the 3 in parentheses. That would help you avoid that. The other way you could avoid that mistake is when you if you do reorder this, the typical order would be 2x ln 3, and then having the 3 to the x squared at the end. That would be the more typical order to do it. But don't ruin good calculus work by poor algebra work, okay? So here's e to the x cubed, so its derivative goes pretty quickly to be e to the x cubed, and then times ln, and then times 3x squared. So more commonly you would see 3x squared in the front, and then e to the x cubed after that. Now mostly what you're going to be asked to do is to apply these in other contextual situations. You'll be asked to find a tangent line using that, or to find when the tangent line might be horizontal or vertical. So you won't necessarily just be asked to do the derivative, but asked to take the derivative and then something else. Okay, the logs. Log derivatives are 1 over, and then whatever u was in parentheses, u will show up again. We have a natural log in this derivative as well. It's in the denominator. And then we have the chain rule, du dx. So that's where the derivative of a natural log has that special case of 1 over u ln, and then times the chain rule of du dx. So it simplifies into 1 over u du dx. But so natural log is the most common one, but this does apply to any log of any base. You just have the ln of that base as part of the denominator. Again, we're not proving this year. You guys just get to be the benefit of just, here it is, here's the rule, use it, but you're not responsible for knowing the proof. The proof is beyond the scope of this class. Okay, so if you're given a log base of 4, then your derivative, okay, Giselle, you want to try it? Yep, let's do quantity 2x minus 1. And then, good job, times 2, okay? So if we simplify this, 2 would be the numerator, quantity 2x minus 1, and then the natural log of 4 can be simplified because 4 is a power, and so we can write 2 ln 2. So that might be something that you would be expected to do. You should be able to do that to ln 9. You should be able to do that to ln 8, because 8 is a power as well. It's 2 cubed. You should be able to do it to 32. You should be able to do it to some of these common power numbers, which then allows you to reduce the constants of 2. So you'd be looking for 1 over the quantity 2x minus 1 times the natural log of 2. So this just gets to matching your multiple choice. If this was a free response question, you would be allowed to leave that in any equivalent form, but if you're looking for your answer to be one of the choices, then you may need to extend that a little bit farther. All right, so here we're going to take it, not just find the derivative, but find the value of the derivative at 0. So we're looking for what f prime of x might be. Okay, Joshua, why don't you take the f prime of x for this one?
1 over the quantity x plus 4 plus e to the negative 3x times e to the...
Well, I need something else still down here.
Oh, Lenny.
Okay. All right. Oops, whatever, change my color. Okay. Times
1 plus e to the negative 3x times Lenny times negative 3.
Okay, good job. All right, so this was a mixture of having the natural log rule and then also followed by the chain rule, which required him to remember the other one. So we're looking at a numerator that's 1 minus 3e to the negative 3x over x plus 4 plus e to the negative 3x. Okay, x plus 4 plus e to the negative 3x. Then we want to do f prime of 0. So now at this point, we'll just substitute 0 in for each of the x values. So 1 minus 3 times e to the 0 over 0 plus 4 plus e to the 0. So that'll be 1 minus 3 over 4 plus 1. So we'll be looking at negative 2/5 as the slope along this curve at the position x is 1. Anybody, any more time on that one? Got it, Josh? Okay. All right. So part of this is also logarithmic differentiation. Okay, and so we would apply a logarithm in something, maybe to something that failed the VLT. Okay, which would be an implicit expression. Okay, that's where we can't get one of the variables alone. So we might use logarithmic differentiation. We might also use it as an alternate to the quotient rule. So that means maybe something that you could do with the quotient rule, but the quotient rule ends up so messy that an alternate to the quotient rule is this idea of logarithmic differentiation. So the name tells you what to do. Logarithmic means apply a logarithm on both sides. One single logarithm on both sides. So it's the natural logarithm, not multiple logarithms on both sides, one logarithm applied to each individual side, and then do the differentiation rules that come after that. So that the title is supposed to help you guide through it. So here's an example of something where logarithmic differentiation allows you, because you can't use the power rule. There are students who try to do dy dx, and they look at this and they go, I'm going to pull cosine to the front, and I'm going to say cosine of x in front of x to the cosine of x and then minus 1, like that. Okay, that's a complete misappropriation of the power rule. The power rule only applies to numerical constants. It doesn't apply to variable constants. So this would be an inappropriate use of the power rule. Instead, you want to use logarithmic differentiation. So you're going to take your natural log and apply it on both sides. So I'll do a natural log around the y side. I'll also do a natural log around the x to the cos x side. So one single logarithm applied on both sides. That's legal because what I did to one side, I did the exact same thing to the other. Now you go through and you apply the rules that are true in logarithms. Now you can pull the cosine of x to the front because that is a property of logs. So now I can have the cosine of x in the front of the natural log of x. So I've created for myself a product. So in logarithmic differentiation, these two steps are the parts that involve logarithms. The next part would be, okay, now I'm going to use my the available differentiation rules I have. So the derivative applied to the natural log of y and the derivative rules applied to the cosine of x and the natural log of x. So I'm applying the appropriate derivative rules. So the derivative rules applied to the natural log of x would be 1 over y times dy dx. And there's a Lenny in there too that I didn't write. Should have written my Lenny, but it's there. Okay, how about on the right side? What are the appropriate differentiation rules to use on that side? Do I just say the derivative of cosine is negative sine and the derivative of the natural log of x is 1 over x? What rule do I need instead? I need the product rule. Okay, I need to use the appropriate rule, which would be the product rule. So the product rule says start with the natural log of x and then multiply it by the derivative of cosine, but add to it the function cosine of x and then multiply that by the derivative 1 over x times the chain rule of 1. And then you have one last step at the end of the problem. If you go back to the original question, what are we asked to find? Yes, Giselle said, okay, find dy dx. Okay, well, I have found dy dx. It's right there. I just need to make sure my dy dx is alone. And so my last thing to do is to get dy dx alone by multiplying by y. And so y will be multiplied by the quantities. I'll put cosine of x over x like that. So now dy dx is alone. It's equal to a big long expression on the other side. And then at the very end, you're going to change out y for what y was originally equal to. You'll substitute and you'll take that y out. And you say, well, y is equal to x to the cosine of x multiplied by the other extended quantity. You don't need to distribute. You don't need to FOIL it out. You can leave it in that factored form and just say that that is what the derivative is. So that's logarithmic differentiation. That was a whole nother day. So what we did in 3 days last year, we're taking, like we did exponentials one day, we did logs one day, and we did logarithmic differentiation one day. Here's another one that would be logarithmic differentiation. Again, because the power rule doesn't work. we cannot pull this rad x to the front and apply a power rule. We need logarithms in order to help us pull that rad x to the front. So we will say, I need the logarithm of y, and then the logarithm of 3x to the rad x. So that allows me to pull the rad x in front of the natural log of 3x. So that's the logarithmic part is applied. Then I'll apply the appropriate derivative rules on each side. So on the left, the appropriate derivative rule is simply 1 over y times dy dx. And on the right, we use the product rule again. So the product rule would be the natural log of 3x, and then the derivative of rad x, which is half x to the negative half, plus rad x times the derivative of the natural log of 3x, which is 1 over 3x Lenny times 3. I'm going to simplify my right side here into a numerator and a denominator. So I'm going to say I would have, in the first term, I'll have ln 3x in the numerator, and I'll have 2 rad x in the denominator, plus, and then what's left in my numerator there is a rad x. And what's left in my denominator is a regular x. And that also is reducible. So the 3 is reduced away. Lenny reduces away. And I'm left with a square root of x on the top and an x on the bottom, which also is reducible. So I could say, I'd really just rather write this in its simplified form, 1 over rad x. You don't need to rationalize that. Either way, this would be fine. If you left it like that, or if you left it in its original form with the rad x on the top and the x on the bottom, either of those is fine. That whole thing would be multiplied by y so that dy dx could be alone. But your final thing would be, okay, just replace y with what it originally was. So that would be quantity 3x to the rad x times the whole other quantity. Okay, any red flags on any of that? Did I go too fast? Okay. All right, this is the last one. For this derivative, I could use the quotient rule. Okay, it would be fine for me to use the quotient rule. I would get an equivalent answer. But it is fairly messy. Can you anticipate the mess? What would be do you think, in your opinion, the messiest part of it? Having to do the product rule while you're doing the quotient rule, because when you get to the part where x cos x and you have to do the derivative, then it's going to be a product rule in that. So an alternate is to try the logarithm rules instead. And so when you apply a single log to both sides, then you can take advantage of some of the log properties. So previously we saw the log property that allowed us to pull a power to the front. That's a log property. In this, there's a log property for quotients. Do you remember what the log property of quotients does to the function? Subtraction. So this would become the natural log of x plus 5 minus the natural log of x, and additionally minus the cosine of x. So it ends up, you are able to separate all of the pieces because x and cos x were both in the denominator, they're both affected by the subtraction. So then I can apply my derivative rules to each of the pieces. So then comes the derivative. So I want the derivative applied to the left side, and I want the derivative applied to the whole right side. So that's going to give me a lot of 1/overs. It'll give me 1 over y dy dx. It will give me 1 over x plus 5 times 1. It'll give me 1 over x times 1. And it will give me 1 over cosine x times negative sine of x. So a lot of the 1/overs. So my right side would become 1 over the quantity x plus 5 minus 1 over the quantity of x and plus the final trig quantity, because I ended up with sine over cosine, would be the tangent of x. All of that as a quantity would be multiplied by the original y. The original y was x plus 5 over x cos x. And that is the expression for dy dx. That is just an alternate to the quotient rule. The quotient rule does work out. They work out to an equivalent expression. It's just a different approach.